Hello mates, in the previous video we had defined what a sidereal day is, and I said in this video we are going to okay, wait, I need to yeah we defined that we are going to we said that we are going to talk now about maybe putting mathematics behind this sidereal day. So that's what we are going to do. Here we just defined what a sidereal day. It starts when V is in upper transit. So let me draw a new diagram. The new diagram that I'm going to draw, I'm not going to draw this ecliptic because we know that this V is just on the celestial sphere as well. So I'm just going to draw the celestial sphere and not the ecliptic. So imagine now a diagram like this. This is South Celestial Pole. This is going to be my North Celestial Pole, like this, and this is going to be where we are on Earth, the center of the side of the celestial sphere. This is a celestial equator, and it's going to go out to the back like that. So now this is what I'm going to do. When the sidereal day starts, when V is in upper transit, that is equal to 0 sidereal hours, right? So 0 sidereal hours occur when V is here. When V is in upper transit, that is where what that is where 0 hours occur. That is where 0 hours zero sidereal hours occur. 0 sidereal hours occur when V is in upper transit at this point. But as the celestial sphere is rotating, V is going to move from upper transit. V is going to come now, maybe V is going to be now maybe at that point. So at 0 hours, V was in upper transit. At this point, let me call it O. So this point here, I'm going to call it O, right? So it's called the O. Let me call it the origin, or point O. So T hours later, now after a few hours, after T hours, V has moved westwards, because west is going to be on this side. It's going to be west, and then this side is going to be east. So V moves like that. It's going to move like that. Let's see, is this correct, Houston? Yeah, this looks okay to me. Yeah, this looks correct. So V has moved westwards through angle of T hours or T degrees, whatever you want to call it, because you know there's correlation between hours, normal hours, and what and degrees. There's a video that teaches how to convert between time and degrees. But after time, this V has gained degrees from what? From O. So let me call this point C. Okay. So now let's put a star. Let a star be in upper transit. So we are now going to let a star be in upper transit when V is now at this point after time T, because the celestial sphere is rotating. So some stars are now going to gain upper transit, some are going to lose upper transit, some are gaining and some are losing. Just like that, as it is rotating, some will go into upper transit, some will not, as it is rotating like that. I hope you understand. So when V was in upper transit, well and fine. But after time T, when V rotated, there is a certain star that was now in upper transit when V was at that point. So let that star be at this point here, because that is what? That is that star's upper transit. So if that is that star upper transit, it will be in upper transit at what? After time T, when V moved to this point. Okay, well and fine. Now let's look at our angles. We have this angle OCV. Angle OCV measured westwards like this. Can you see that angle? That angle OCV, when we measure it westwards, if you remember well, when we're talking about the first equatorial system, the first equatorial system is basically measuring an angle. The first equatorial system, we measured something called the hour angle. We measured something called the hour angle, represented by what? By HA. So we said our angle was, let's say, the degrees what? It was our angle was our angle were like degrees measured from what? From the origin O to that point where what? To the point, it was M. In our first equatorial system, that point was M on the celestial equator, and we created our angle OCM. But in this case, we have our V, and the V is on what? Is on the celestial equator. So we can measure our angle OCV. And our angle OCV is going to be our angle. Why is it our angle? It's because we are measuring it, the angle from what? From this point O. In the hour angle system, O is the point where the celestial meridian cuts the celestial equator. So where the celestial meridian cuts the celestial equator, we have our origin, isn't in the first equatorial system. If you don't remember, you can go over that video again and you see how we defined our origin in the first equatorial system. So this is going to be our origin, and the coordinate that was measured from this particular origin O was called our angle, up to where what? Where the M, but here where the V is. So OCV is the hour angle of this particular point being called what? Being V. So here OCV is equal to our angle, and I'm going to say our angle of V like that. This is the hour angle of V. I hope you understand. I hope I haven't confused anyone. If I have, please tell me so that at least I explain this principle again. This is going to be the hour angle of V measured through west, because we are measuring it from an origin that measures our angle. And the angle here it's making sense to call it our angle of V, because that is how we measure our angle. You can go over the video that defined our angle. So this is going to be our angle of V, isn't it? And then now here, but we have another system. We have another system that used a different origin, the second equatorial system. In the second equatorial system, we used V as the origin. We used V as the origin. And we said, okay, we are going to measure V, and V was going to be VCM, the M being where our circle of the star cuts the celestial equator. The M was going to be where what? Where our stars, our angle cuts. If our star was going to be here, we're going to put our M was going to be somewhere here, and then we're going to measure VCM. But then our VCM was measured through east. Now, what was that name of that coordinate that we measured in the second equatorial system? VCM was called the right ascension. So we measured something called right ascension, right, of a star, and we called it RA, and we represented it by RA, isn't it? So by that, can you see now, I've used the hour angle origin. Now let me use the V origin. When I'm using the V origin, I'm going to say, oh, I'm supposed to measure VCM. I'm supposed to measure VCM, the M representing the what? The point where the hour circle of the star cuts the celestial equator. But let's see, this star here, this is the observer's meridian, yes, but it is also an hour circle, because it is the one that is connecting the south celestial pole and the star and the north celestial pole. So this is what? This is that particular. We are lucky now because the celestial meridian is coinciding with the hour circle. Because why are they coinciding? Because the star is now in upper transit. If the star was here, our hour circle was going to be like this. That's how our circle was going to be, and our M would have been there. But as it rotated, this was one particular point in time. As the celestial sphere rotated, this hour circle also moved, up until when this is now in upper transit, which means the hour circle is now coinciding with the celestial meridian on this side. So now we are going to measure VCM. Our M is now coinciding with the origin, because that is where the hour circle is cutting the celestial equator. So our celestial equator is being cut here, which means this point is also M, the point M for that star. For this star, this is point M. So right ascension was being measured from the point V up to M. So it was VCM. So here, instead of saying M, let me say O, which is the origin. So our angle VCO measured eastwards like this from this origin in the second equatorial system is going to be equal to the right ascension of the star. I think you remember this from the second equatorial system. We have taken this from the first equatorial system, this from the second equatorial system. I hope you remember these two concepts. If you don't, just go over those videos. They will explain well what I'm saying here. So now that we have our two angles, can you see that the angles are measuring the same thing? They're measuring the same, let me say, distance in chords. VCO is equal to OCV. Therefore, when the star, so when star is in upper transit, when the star is in upper transit, as is our case here, when the star is in upper transit, the hour angle of V is equal to the right ascension of the star. As we can see here, the hour angle of V is equal to the right ascension of that star. So what does that mean? Let's see what this basically means. This basically means, let me get another. Okay, let me see where I have my. I'm missing my plastic papers. Okay, I found them. Okay, now what this basically means, what this part here, this last part means is. Do you know when we talked about what about sidereal time? Sidereal time was being measured from when V was in upper transit up to where it was. You see, up to where it was. What time did we say this situation when V is here? We said it's now T sidereal hours, right? It's now T hours after. This is a situation when it's T hours afterwards, after V was in upper transit. So basically, here our t was equal to 0 when V was here, but when V was there, our t was equal. Let's say our time was now equal to t, and then our s was now in what? Was now in upper transit. So basically, on our sidereal clock, since this one was measuring 0, and when it was here, it was now t. So we can basically know the period that is passed, maybe 2 hours, 2 sidereal hours that is passed for V to be at this point. And when V is at this point, we see that is when S is now in upper transit. So basically, what I'm trying to say here is every star will have its associated sidereal time, because as V is rotating, giving us a new sidereal time, another star will be in upper transit. As V is rotating again, giving us a new sidereal time, another different star will now be in upper transit. So every particular star has its own associated sidereal time. So here in this case, on the sidereal clock, we are measuring how far V is from upper transit, right? We say T hours. But what star is now in upper transit is this star S. So the sidereal time of this particular star is T, because that is the time being given by the sidereal clock. So therefore, my sidereal time of upper transit star. So we can say the sidereal time of upper transit star is equal to the right ascension of that particular star. As we have seen from this here, this hour angle of V is measuring the sidereal time, because our angle is measured how far is V from the origin, and V was measured at the origin. The sidereal time was 0. When V started moving, gaining our angle, it was gaining sidereal time. It was gaining sidereal time. It was gaining on the sidereal clock. So this hour angle of V is equal to how many hours there are on the what? On the sidereal clock. So it's basically the sidereal time. So our angle of V measures sidereal time. I should have put that up there. Our angle here is measuring sidereal time. I hope you understand. If you don't be afraid to just ask me to explain this concept properly. And yeah, I don't think it's coming up properly because of the way I wrote it. But the sidereal time is measured by our angle of V. But what is our angle of V equal to? It's the right ascension of star. So the sidereal time of upper transit star is equal to right ascension of that star. And so now we can come up with what? With another deduction. Imagine now after another extra hour or 2 or whatever, this is going to be, let me draw it from the area of view. From an area of view, our situation from an area of view originally was O, and our M was here. That was the original situation, right? This is from an area of view, and our V was here. That was the original situation. Our M was coinciding with what? M was coinciding with O. But now look at this new development. After rotation again, after a few minutes or hours, our M will be there because our star, the particular star S, has rotated as well as V. V would have also moved. V would have also moved from where it was. V would be here because V moves with the celestial sphere. So can you see we have our angles now? We have our OCV and we have our OCV and we also have our OCM. So now let's calculate our angles. From this, we can calculate our OCV. Our OCV, which is equal to our angle of V. OCV, which is our angle of V, is equal to VCM. Can you see VCM? But it's measured. VCM like this is measuring right ascension of this particular star. As we talked about in the others, under other videos, VCM will be equal to the right ascension of the star. And this one, OCM, is measured from O, so it's the hour angle of what? Of the star. OCM is equal to hour angle of star. And as you can see here, our angle of V, OCV, is equal to VCM plus OCM, as you can see here. So my hour angle, I shouldn't have said hour angle V. Here I should have said maybe OCV. Time is almost up. I think I'm left with like 2 seconds. So let me just quickly do this. I'll continue. All right. Let me leave it here and then continue in the next video, and we'll see an example in the next video. All right. Stay tuned for that one.